Hello, this is Concrete Path, and the lecture for this is that what we call as stages of stress analysis. Stages of stress analysis in this stress concrete. So we have two different stages of stress analysis. One is that we call that as transfer stage, transfer stage, and second one we call it as final stage, or we can say this is the service stage. Final, or we can say this is the service stage. So, so we would say actually what's going to happen. First of the thing is that how to apply the stress in the steel wires. How do you apply that pre-stress of some stress? How do you apply that stress to to a steel tendon? How do you apply that stress? We call it as initial stress. P naught means initial stress in the tendon. Stress in the tendon. How do you apply that? I would say because of any method, either pre-tension or post-tension you apply, you elongate the wire, you elongate that strand. Because of that elongation, so I would say because of the strain developed, delta L by L, elongation of delta L divided by total length of L, and we have that modulus of elasticity of that wire, and because of that you would get stress developed in that wire, pre-stress. Let's say that because of that jack, you had developed some elongation of 120 millimeters, and the total length of wire was, let's say total length of the wire was 1600 that I would say 16 meters, 16-meter wire, and I would say the modulus of elasticity is 2 into 10 to the power 5 megapascal. Okay, we would see how much stress has been developed, in the wire. A stress of 1500 megapascal. If I say what is the total force that has developed because of this initial pre-stress of P naught, I would say there was some initial pre-stress force of P naught, initial pre-stress force of P naught was developed. That was equals to area of the steel wires into that stress in the steel wires. Stress in the steel wires. Let's take that area of the steel wire was 2400 millimeter square. This was the area of the steel, and we have P naught equals to 1500 megapascal, and the total force comes to be equals to 3600 kilonewton. So this is the case when we are saying that this is the initial case, that's what we call it as transfer stage. But one thing is there, there is losses. We call that as losses. So when there are losses, so something is going to change. So when there are losses, we are going to see what's going to happen now. So we say that there is losses. Losses occur because losses occur in elongation. That is, in elongation, losses occur. Losses occur in elongation because of either we can say because of that during the because of it can be it can happen during the pre-stressing, during the tensioning of the steel, during tensioning of the steel wires, or it can also happen during the transfer of P force, during the transfer of P force from steel to concrete, from steel to concrete, from steel to concrete. So these are the two possibilities that how your elongation can be lost. Some of the elongation can be lost. So you are stretching the wire some delta, but because of some reasons, because of the reasons of that, when you tension that, there is a chance that it can slip, that wire can slip again. Little bit of deformation can be lost. Or when we transfer the stress, when we transfer that P force to the concrete, and then at that time also there might be shortening of that concrete because of the transfer of force, and there might be loss of that stress in the what you call as wires. There is a chance we are going to see those losses also. So these are the two losses, and these are the two reasons. And I would say, let's say now there is some loss of elongation. And let's take that elongation loss. Let's say that the elongation loss, delta loss equals to, let's take that as 30 millimeters. Out of the total 120 millimeters we provided, out of the total 120 millimeters we provided, let's say the loss is 30 millimeters. And I will calculate how much stress has been lost. How much stress has been lost? I would say that is, this is 30 millimeters have been lost. Out of the length, total length was 16 meters, and we had that modulus of elasticity as 2 into 10 to the power 5. So your loss of stress is 375 megapascal. And similarly, I would say, what is the force we have lost? Force loss is equal to 375 into 2400, that steel area. So that's 900. That's 900 kilonewton force of, that's this amount of force we have lost. So I would say the final force is equal to, final force in the wires is equal to, initially it was 3600. So I would say 3600. This was the initial case P naught minus some loss of P loss equals to 900. So finally it is 2700. So we can also represent it. We represent that that percentage of the loss, percentage loss, we represent it as that percentage loss is represented as percent K. That means how much percent of that total stress or total force has been lost. And we would say in this case your percentage of the loss is equals to 900 kilonewton divided by total force was 3600 kilonewton, and into 100 I would say this is the percentage, that's 25%. 25% of the, what you can say, total stress or total force has been lost. Total prestress force or total prestress has been lost by some 25%. So this transfer because of the transfer of that stress, because of the transfer of that P force or stress from steel to concrete, at that time also we have some losses 1, and during the tensioning of the steel itself we have losses 2. So the loss 1 plus loss 2 contributed to some value of K, that is percentage loss. And based on this we say we have 2 different stages of analysis for the stress calculations, because your P force is getting changed, so that means your stresses are going to also change. So your first transfer stage, it talks about that we are going to calculate that we are not using the pre-stress beam for the actual loads. We are just calculating the stresses because of the dead load, because of the P force and its corresponding eccentricity. We are not calculating live loads, effect of the live loads. So we are calculating only at that stage when there is only dead load, there is only P force, there is only eccentricity of that P force. So if I take a general beam that we have, if I take a general beam, there is some dead load, live load, there's some dead load, there's some dead load, live load, and there's some cable at a that cable is placed here in a parabolic way, and the cross section is a T-shaped cross section. If I talk about the midspan, I would say there's some eccentricity from the neutral axis. So if I calculate for that, I would say for the first case, that is transfer stage, if I calculate the stresses for the transfer stage, first stage, it says that we are going to take the initial pre-stress force. So let's say that the neutral axis is here and the force is acting on here. This is called as P naught, initial force of P. Till now we are not, we were just writing that P naught as just as a P, because we are not talking about those losses and all those stages. We were saying this is some P, and in this case we are writing as P naught, that is the initial pre-stress force. So it's applied at some eccentricity of E. That means the stresses that gets developed is equals to P by A. Yeah, we can write P naught by A, and actually it's P naught cos theta, because the cable is not straight, it's in a curved way or a parabolic way, so it is a P naught cos theta by A, P naught cos theta by A, P naught cos theta by A, P naught cos theta by A. That is compressive, direct compressive stress. And one more is there, because of the hogging PE, we have top tensile, bottom compressive, top tensile, bottom compressive. I would say this is your P naught cos theta E, and divided by I by, we write that your I by y bottom we write it as z bottom, and your I by y top we write it as z top. That is the section modulus of that top side, and section modulus of bottom side. That is moment of inertia about the neutral axis. Moment of inertia about the neutral axis divided by that extreme fiber distance from the neutral axis of for the top side. This is that's y top. Y top is that how much, this is the y top, we can say this is y top. From the neutral axis, how much is the distance of the extreme fiber? That's y top, and this is your y bottom. Okay, and directly we can write z bottom, z top. We can directly write that. Right, let's write that z here. This is z bottom, and at the top we can write is p naught cos theta e by z top. And third stress is there. Third stress is there because of the dead load we are calculating. Dead load causes sagging moment, so top compressive, bottom tensile, and that we can write m dead by z bottom. Here we can write m dead by z top. These are your stresses, and the resultant of these three would cause some stress diagram such that we say that ideal stress condition should be such that we have some stress here, compressive stress here, some value, but at the top we should have some zero stress. This is some ideal condition. It can be different also. Let's say it's not exactly zero at the top. It's not exactly zero at the top. I would say there might be some chance that deviation might be also there. Let's say these are the three different possibilities that stress can be either tensile, it can be either tensile, it can be either compressive, a little bit of value there, but our ideal condition is that I'm going to write that as by that green color. Ideal stress condition for the initial case. Ideal stress condition for the initial case. I don't want tensile stresses in the concrete. That's because concrete is weak in tension, so I don't want that to be happening there. So that's the ideal stress condition. That that tensile stress is zero. Sigma t is zero. I want that. That's ideal stress condition. Second thing is that second case of the loading is that second stage we call it as final or service stage. Service stage means when there is the external loads that are applied here. So the beam is designed for the some service loads, that is live load, superimposed loads of dead load, superimposed dead load, or it can be live load also. So those we can call as service loads. So for those loads we can say this stage is called as service stage. So we have to account all those loads. We have to account all those loads for the second case, that is transfer stage. So for the second case, that is transfers, yeah, that's the final stage. I would write final stage, or we can write service stage. For that, your losses has to be accounted. Yes, let's say there was some cross section of the beam, neutral axis is somewhere here, and we have some eccentricity, and there is some force of P. But this one I would call that, because there is loss of K percentage. This is the percentage loss of force. That means final force is only how much? Final force is only force. Yeah, we are writing that actually that K. This is not the K actually. This one. Once we write that percentage K, this is not the. We are writing that percentage K in this way. Let's have that again. Let's have that again. What we are going to do? I'm saying that you got final force of 2700. So that 2700 I'm going to write that as K times P in P naught. I'm going to write this one as K times P naught. That means percentage loss is 25%. Percentage loss is 25%, but your K value is actually 100 minus 25%. 100 minus 25, that's 75%. K is 75%. That means 0.75. So K we are going to write it as 0.75. We are not going to write it as 25%. I would write this one as percentage loss. This one I'm going to write as percentage loss. That is how much loss has occurred out of the total force. So that is percentage loss. That is 25%. And after that I'm going to write what is the K value. I'm going to write that is equals to 1 minus 25%. That is 0.25. So finally your K value is how much is left. K represents how much is left. That's your K value. So that will represent as that final force is equals to K times P naught. how much of the initial force has been left, that is your K times P naught. So I'm going to write that here, K times P naught. So that force of K times P naught cos theta is applied at some eccentricity. So our stresses would be that this is your positive Kp naught cos theta divided by a cross section, and second stress is there. Let's say this is neutral axis. So here we have top tensile, bottom compressive. This is K times P naught cos theta, some eccentricity E divided by Z bottom, and at the top I can write Kp naught cos theta E by Z top, and we are going to write that all those loads. So I can directly say that because there is some dead load, there is some live load, so I can write that there is some load of all those loads. There is some moment because of all those loads. So I can write M all, Ma. That means M all, M all, M all. Okay, M dead plus M live, and their effect I can write that combined. I can write the combined effect here. Top compressive, bottom tensile. This is minus plus M all by Z bottom, M all by Z top. Then after that, the final resultant of those three, I want that ideal stress condition to be there. That I want stresses in this way. This is the ideal stress condition. Ideal stress condition. Ideal stress condition for the second stage. That I want no tension. I want no tension in the bottom fibers. I want no tension in the bottom fibers, and there might be little deviation also. If I want to allow a little bit of tensile stresses also, so this is our condition for that. And if I want that no compress, no idea, no ten, if I want a little bit of compress also, so these are three possibilities. But our ideal stress condition is that tensile stresses is equal to zero, So that's the second stage. So if I write that final conclusion is that in the transfer stage, so in the first stage, that is transfer stage, when we are transferring that means we are transferring the stress from steel to concrete. That is the transfer stage, that transfer of that stress from steel to concrete. At that stage there is losses, but we say losses, we ignore losses. No loss is there. That means we are calculating for the actual P naught. So stress is based on the actual P naught. So we assume no losses. We say there is no loss, but there is some loss also at the transfer stage. So here is this assumption that we calculate for the no loss. Okay, no loss is there, and we account effect of P, its eccentricity, and dead loads. These are the things we are going to do here. And in the final or transfer stage, we say that there is some loss. Loss is accounted. So final force is Kp naught, and its eccentricity we are calculating the stresses based because of that also, and because of the dead load, because of the live load. So we are calculating stresses because of the moment, all moments. So okay, so that's the difference between these two stages. That is the difference between these two stages. So let's try to take a problem. Let's try to take a first problem. Let's try to have the first problem of this stages of stress analysis. This is your post-tension pre-stress beam, pre-stress concrete beam, and we have span of 20 meters. 20 meter span beam, 20 meters. Okay, there's some live load also. Live load of 12 kilonewton. There is some live load, 12 kilonewton per meter. Okay, so all the data is provided. That we have some cross section. Provided to you. Cross section provided to you. This one is 500. Thickness of flange is 150, and bottom flange is 200, and we have this width only 300. So, and the 650, I would say this one is your width of web, that is 150, and the depth of the web is that's only 650. Okay, and neutral axis is also calculated. That is from the top, neutral axis is somewhere here at some location of somewhere here. Let's say this value is 455.6 millimeters. That's the location of neutral axis. And I can say that this part is how much? How much is this part now? If I want to calculate now, how much is this value? That is total of 150 plus 650 plus 200 minus 455. So I can solve for that one. I can solve that one also. 150 150 plus 650 plus 200 minus 455. 455.6. That's 544.4. So this is 544.4 millimeters. So that's your y. I can write this is your y bottom and this is your y top. Okay. Section is unsymmetrical, so we had to do different values of those y values. Now the steel is placed somewhere. Steel is placed somewhere from the bottom at 100 millimeters from the bottom or soffit. So let's say there is some soffit from the soffit at 100 millimeters. So if this is 200, I would say 100 is somewhere here. So here we have placed the steel bars at a location of 100. This is 100. So can you tell me what is the eccentricity? Can you tell me what is the eccentricity? What is the eccentricity we can have? This part is your eccentricity from the neutral axis. This is our eccentricity E, and that we can say that is y bottom minus 100. So that's 444.4. 444.4 millimeters. Okay. So finally we got this one. And now that we can say what is the problem all about? What is the problem all about? We need to calculate the stresses. We need to calculate the stresses at the top and at the bottom, but for two different stages. One is your first stage, that is transfer stage. Second one is that final stage, final service stage. So at two different stages of that beam, we have to calculate the stresses because of the different loadings we can have. And one more thing is there, that percentage loss is 15%. Percentage loss of either we can say force, Prestress force, or we can say percentage loss of Prestress. That is 15%. 15%. That means K value is equals to 0.85. Can we say that? Your left portion of the total stress is 85%. And all the data is provided to you. All the data for the cross section is provided to you. That Ixx for this cross section is 265.334 10 to the power 8 millimeter per 4, and Z top for this section is 5.8238 10 to the power 7 and Z bottom is also provided to you. That's 4.8739 10 to the power 7 millimeters per 3. Okay. And area of the cross section is also given. All the stuff is provided to you because the calculation is not about calculating the I, all that stuff. Problem is about the calculation of the stresses. Area of the cross section is 232,500 millimeters square. And one more thing is there. Dead load is there. Dead load is equals to 25 into area of the cross section. So that is equals to dead load 5.8125 kilonewton per meter. And live load is there, we also know. And we say that because of that beam is simply supported. Because of the beam that is simply supported, we have 20 meter span. UDL is there, live load. Dead load is also there, so we calculated the moments also. Dead load moment. Dead load moment is there. Dead load moment is equals to 290.625 kilonewton meter. And live load moment you can solve, that is also 600 kilonewton meter. So these are the data that's all provided to you. This is the data all that's provided to you. Now we need to calculate the stresses at the top and bottom for two different stages of stresses. And we can say that we are calculating at the midspan. Let's say that the cable is straight. We don't worry about that because we are taking a particular section. Of a beam at which what you call as we have eccentricity here. Let's say we are calculating for the midspan. Here the eccentricity is there. Let's say that the cable is straight. Let's assume that cable is straight. We are calculating for the midspan. Okay. Let's go for that now. So first stage we can write, first stage, that's your transfer stage. So we had this section, neutral axis is somewhere here, and P force is applied somewhere here, and we can say this is some P naught force, P naught at some eccentricity E. So I can have the stresses, I can take the stresses. I would say first stress is that we have P naught by area cross section, and second is that because of its eccentricity, we have negative positive P naught E by Z bottom. At the top we can write P naught E by Z top. And third stress is because of the dead load. Because of the dead load we have top compressive, bottom tensile. Yeah, top compressive, bottom tensile. Top compressive, bottom tensile. Yeah, this is neutral axis. So I would say this is M dead by Z bottom, and this is M dead by Z top. So we can calculate now the stresses. We can calculate the stresses. So I would say your stresses at the top, your stresses at the top for the first case is that P naught by A minus P naught by A minus P naught E by Z top minus P naught E by Z top. And third one is that positive M dead by Z top. And because of the second, for the second case, that's stresses at the bottom, I can say that is F bottom, and that is equals to P naught by A, that's plus P naught. In place of Z bottom, we have to replace Z top here, Z bottom. In place of Z bottom, Z top, we have to replace as Z bottom. And for this case also, this one was your positive, and we have to replace it as negative, and this has to be changed by Z bottom. And all the data is provided to you. This is all the data that's provided to you. Let me try to calculate those. I would say, what is the value of P? What is the value of P? What is the value of P we have? Yeah, we need to see what is the value of P. So the value of P can be solved in this way, that we have a cable area. We have a cable area of cable area is 1385. We have a cable area of 1385.44 millimeters square, and we have a stress in the cables. Stress in the cables is 1100 megapascal. So we can say, what is the P value? We can have initial pre-stress force. Initial stress force is equals to that's 1523.984 kilonewton. This is the initial pre-stress force. 1523.984. So I can have those two different values. I can calculate those different values. Your 1523.984 kilonewton divided by area of cross section. That was also provided to you. Area cross section of the concrete, that is 232,500 millimeter square. This is your stress of P by A, and that is equals to 6.55 megapascal. And second stress is there, P naught E by Z top. So I'm going to calculate P naught E by Z top. That's 1523.984 kilonewton. Eccentricity E was equals to 0.4444 millimeters, or we can write meters here. And Z top was given to you. Z top, that's 5 we can write that here. That's 5.8238 10 to the power 7 millimeter power 3. So that you can convert then afterwards, such that your stress is equals to 11.63 megapascal. Similarly, you can write P naught E by Z bottom. That is same at the top, and bottom we can change by that value of Z bottom, 4.8739 10 to the power 7 millimeter power 3, and that stress would be more as compared to the initial one. That would be 13.897 megapascal. And because of the dead load we can solve. I would say M dead by Z top is equals to 4.99 megapascal, and M dead by Z bottom is also equals to 5.964 megapascal. You have to substitute these values You have to substitute these values here in the equations to get the stress, final stresses, resultant stress. So your dead load has been calculated earlier. It was given to you. Live load is also given to you. Dead moment and live load moment. Okay. Now you have to substitute those values here, and you can say your F top is finally stresses at the top is equals to 6.55 minus 11.63 plus 4.99. Stresses at the bottom is 6.55 plus 13.897 minus 5.964. This is minus 0.090, and this one is positive 14.483. So final stress diagram would be that this is your 14.483, and there's some negative stress at the top, and this is your stress diagram. This is your stress diagram for the initial first transfer stage. This is the first case. This is the first case that we have. Okay, now we need to take the second case. That is the final stage. For the final stage, we need to calculate now. For the final stage. So for the final stage, let's have that. If I write that final stage here, final stage. So final stage would be here. Final stage. That means the force that is here, that is K times B naught now. The force that would be here, that is K times B naught, because there is some loss, and K value of K is 0.85. I can write K times P naught by A. Here we have to multiply every time, every P naught we have to multiply with K. Every time you see P naught, you have to multiply with K. And there's one more thing. We don't have to only write M dead, we have to write M all. We have to write M live also. There is live load moment also. So that's tensile and top compressive. So here we have M live by Z bottom, Z top, and at the bottom I will write M live by Z bottom. So we need to also add that stress also. So for the top, now we can write the equation. We can write the equation here. We can have a multiple of K times here. K times, in this case also K times. All the other stuff that is constant. And we have to add one more term that's at the top. We have to write M live by Z top, and for the second case we have to write M live by Z bottom when we calculate stresses for the bottom. So we need to now say what is the M live by Z top and M live by Z bottom. So we can solve those values also. Then that coming out to be equals to M live was your 600 kilonewton meter, and your Z top was 5.8328 10 to the power 7, 5.8328 10 to the power 7 millimeter cube, and that was your value of 10.30, and this one was your value of 12.31 megapascal. Now we have to add these two values also in the final calculations. So your stress would get changed now. Your stress has to get changed. If this was K, let's go from the first one, that's P by A. So we have to multiply now K times. So we have to multiply that value of 0.85 such that this stress becomes now, equals to now, yeah, we can keep that. This stress becomes in this fashion, okay? And this one we have to multiply K, and similarly here we have to multiply 0.85. So this would get changed. And similarly third one we have to multiply here K times. So we have to multiply that 0.85 here, and dead load is there. So for the first two stresses we have to multiply that. We can directly say this is, we have to multiply 0.85 here. In these two parts we have to multiply value of K, because it's accounting that P and its eccentricity. So first one and second one, that's why we multiply that 0.85 for the first and second part. After that, this is the effect of dead load. We don't have to change anything with this one. After that we have to add one more thing, that is because of the live load effect. We have to add the effect of the live load. So I would say at the top we have tensile. At the top we have compressive, that is positive M live by Z top. M live by Z top was 10.30. M live by Z top, and I would say M live by Z bottom. M live by Z bottom is here. That is equals to 12.31 megapascal, and this one is your negative value. So we have to keep that negative. So finally your final stresses would be equals to 10.97 megapascal, and bottom one is that minus times 0.6241 megapascal. So your final stress diagram is in this fashion. Some negative, and from this side we have some what you call as compressive, that 10.97 at the top and negative 0.6241 megapascals at the bottom. So these are your two different stages of the stress for this part of the problem. Okay, let's take that one more. Let's take one more problem. Let's take one more problem. Let's take that second one. So we have a simply support beam, 6-meter span. Simply support beam, 6-meter span, 6-meter span, 6-meter span. There is some live load. Live load is there. Live load of 11 kilonewton per meter. The cross section is that we have T section. We have a T section with the top width as 500 and flange depth 100 millimeters. Width of web 120, and this one is your 300 depth of the web. This is 300. Okay, this is the cross section we have of this beam, and we need to say what is the required value of find the value of P. Find the value of P and eccentricity of that P from the neutral axis. And cable, you have to consider the cable as straight. Let's say the neutral axis is, after calculation, neutral axis is somewhere here. So let's say neutral axis is somewhere here, because we have more area on the top side. So let's say this is the neutral axis, and based on that, I would say there's some eccentricity of E, and the cable is straight. Cable is straight. This is some cable. Cable is straight, and cable is also straight. Cable is straight. And we have to say what should be that value of P force that we are going to apply at some eccentricity of E from the neutral axis, such that your stresses in concrete in compression. So in compression we have that it should not be that means it should be less than 15 megapascal, and stresses in concrete in tension should be equals to 0, or we can say it should be either greater than 0 or it should be less than, it should not be less than 0. That means there should be no tension in the concrete. That's we don't allow any tension in the concrete. We don't have to allow any tensile stresses in the concrete. That means the stresses at that fiber should be either compressive or it can be equals to 0. So if we take the two different stages, so we are calculating actually for the two different. So we need to say what is the value of P and E for two stages of stress, two stages of that stress analysis. Okay, so that means based on the criteria that's provided about the stresses in the concrete, that means if we talk about the first case, that's transfer stage, your ideal condition that we had to achieve is that at the top we have to ensure that there is no tensile stress, and at the bottom we should say the compressive stress that is positive 15 megapascal should be there. And for the final stage, your stress condition should be such that at the bottom we have zero tensile stress, and at the top we have some compressive stress maximum we can take as maximum value we can have, that is 15 megapascals. So we can apply the conditions. We can apply the conditions to get the value of P and value of E. So we have to calculate that. So first step is that calculation of that I neutral axis, location of that Y bottom, Y top, Z top, Z bottom. So we need to calculate all that stuff. Let's go for that. Let's calculate the neutral axis location. So area of the cross section is total area of the cross section you can have 500 into 100 and plus that. So that's area of the cross section is 8600 millimeter square. It's the area of the cross section of concrete. Okay, and we have to place some that P force somewhere here. That is some eccentricity should be there. We don't know the value of E, and we don't know the value of E. Let's go for the calculation of neutral axis from the top. Let's say this is Y top. Let's say this is your Y top. Location of neutral axis, Y top. This is neutral axis. So first step is that location of Y top. That's a total area 500 into 100, acting at 250, plus second area is that there 300 into 120, and your value of that centroid from the top is equals to 100 plus 150. 100 plus 150, that is 250, divided by total area of the cross section, that's 86000. So finally you would get value of y top 133.72, and your y bottom can be also solved as total value we have. What is the total value we have? Total depth, that is 400. So we can write this is your 400 minus y top. That's equals to 266.28, and y top was given to you as 133.72. So we got the values of these one, and we can calculate the moment of inertia about the neutral axis. That is b d cubed by 12, b d cubed by 12, b d cubed by 12 plus ad square, a into d square. That's its centroid is here and neutral axis is here. So I would write 133.72 minus 50 whole square. And third one is there, that area of that rectangle, that's bd cubed by 12, bd cubed by 12, bd cubed by 12 plus ad square, a d square. What is the value of d? I would say the centroid for this part, for this rectangle, is somewhere at 150, and yeah, I would say this is 350. Okay, this is 350. This is 300. The yellow line, this is 300. And I have to go to the centroid. Let's say centroid is somewhere here at 150, and I know that this is at 262 to 266.28. I can write look, difference of those two is 266.28 minus centroid is at 150 whole square. This is your INA, that's coming out to be equal to 1148.88 10 to the power 6 millimeter power 4. And that from that we can calculate z top and z bottom. Z top, z bottom. Z top is I neutral axis divided by y top. Y top is 133.72, and your z bottom is I neutral axis divided by y bottom 266.28, and finally your values coming to be equals to, let's keep that as it's, and let's go for the calculations of the stresses now. So we have to get the value of P and E such that your stresses, your diagrams are in this way, based on the criteria we have. So let's try to calculate for the first case. That's our resultant diagram should be a triangular such that at the top we have 0 and at the bottom we have 15. So I would say you had this T beam, you had this T section beam, neutral axis is here, your load is applied somewhere here at P naught, there's some eccentricity of E, and let's calculate for the transfer stage. So your force at the transfer is P naught. So I would say the first stress is there, that's P naught by A, area cross section, and after that we have top tensile, bottom compressive. So this is P naught E by Z bottom, this is P naught E by Z top, this is tensile, this is compressive. After that we have to ensure the effect of the dead load now. Effect of the dead load, top compressive, bottom tensile, M dead by Z bottom, M dead by Z top. So that's negative. Yeah, this is positive, this is negative. And we need to calculate the dead load effect also. Dead load moment. Can you calculate the dead load moment? So dead load moment can be calculated as M dead is equals to 24, we can take 25 kilonewton per meter cube into the area of cross section 86000 millimeter square. This is the weight per meter. This is the weight per meter, and we have to multiply that L square by 8. That's equals to M dead. M dead is what you can call 9.675 kilonewton meter, and your live load moment can be solved as 11 into 6 square by 8. 11 into 6 square by 8, that's coming out to be equals to 49.5 kilonewton meter, so 9.675. So we have this value here, 9.675. So we can write this one is your 9.675 kilonewton meter divided by Z bottom. So you need to solve for those values of Z bottom, Z top, and I can say that your stresses at the top, we have to ensure the condition that we have to ensure the condition that a resultant of these three is having a diagram in this way, that stresses at the top is 0, stresses at the bottom is plus 15. So we have to write that condition now. I would say the first condition is there, that stresses at the top is equals to P naught by A plus, that's minus P naught E by Z top plus M dead by Z top equals to 0. And second condition is that F at the bottom is equals to P naught by A plus P naught E by Z bottom plus, yeah, minus is there, M dead by Z bottom. That should be equals to plus 15. Plus 15, that is concrete compression 15. So based on these, we have to get the value of P and E. So I would say that we have two equations and we have two unknowns. P and E, we have two unknowns and we have two equations. We have to solve that. So we need to substitute all those values we have. All those values we have to substitute. We have to substitute all those values. So let's try to calculate that. So let's try to have those values here. So let's try to calculate that. So first case is there, that stresses at the top, we have to ensure that sum is equals to 0. So I would take the first case, that's P naught by area of the cross section. P naught by area of the cross section was given to you. Area of the cross section 86,000, 86,000. So we have to keep that. We have to ensure that we are calculating for the P is in kilonewton and E is in millimeters. We have to take this units of those in such a way that we have to ensure that we can get the value of P in kilonewton and E is in millimeters. So I would say this is your 86000 is in millimeters, so that's millimeter square. So I'm going to keep the units in kilonewton and millimeter square. Let's try to have the units in all the units in either kilonewton and all the units in millimeters. Let's try to keep those in this fashion. P naught by 8600, or either we can take this one as newtons. Let's take this as newtons. I can keep it as newtons. So I would say this is some P naught newtons. Let's write that this is newtons per millimeter square. So first case is there, and second one is there, minus times P naught eccentricity E, we don't know the value of E, divided by Z top. Z top is equals to I neutral axis divided by Z top, that is 133.72, and this unit is millimeter cube Z top. And third one is here, plus of M dead. Your M dead was 9.675. This was kilonewton meter, so I have to multiply that 10 to the power 6 such that it becomes newton millimeters, divided by that same value of Z top, 1148.88, 10 to the power 6 divided by 133.72, and this is in millimeter cube, so that equals to 0. So based on this, you can simplify it to get an equation in this way, that 99.9 P minus P times E plus 9.675 10 to the power 6 equals to 0. This is one of the equation we got from the first condition. And second condition we have to solve for, that P naught by A. So this is P naught by A. After that we have plus, we have to add here plus P naught E by Z bottom. So P naught E by Z bottom, that means we have to replace this that Y bottom. All the stuff is same, that we need to just change that 266.28 here. And third one is there, M dead by Z bottom, and this is negative, M dead by Z bottom. So Z bottom only we have to change that 133.72, so that's 266.28. So after that we have the second equation. We can get the second equation as 50.14 times P plus P times E, then negative times 9.675 10 to the power 6 That is equals to, yeah, and that equals to 64718341.6. And finally, if I add those two equations, because I have that, I can see if I add that equations, our this part gets cancelled. If I add the equations 1 and 2, 1 plus 2, adding equation 1 and 2, I can get the resultant that I can get the net value that your P can be solved as. So finally, I would say 150.07 P is equals to 64718341.6. So this is the value we have. Actually, the equation you can still solve. What is this coming out to be? And finally, your equation is finally coming out to be that P comes to be equals to 431.25 kilonewton. And after that, to calculate the eccentricity, we can substitute in either of the equations. We can substitute in either of the equations the value of P such that we can get the eccentricity. So we can solve it 99.9 P plus 9.675 10 to the power 6 divided by that 431.25, and that's your value of eccentricity 122.33 millimeters. 122.33 millimeters. So these are the values we got. We got the values of P as 431.25 and 122.33 kilonewton 33 millimeters. Now this was based on the case 1, that was your stage 1 transfer stage. Now we got the values of P and E. Now we need to say that we are going to verify these for the second case. For the second stage of analysis, we are going to verify these values whether our stresses are under limits. We need to check for this particular value of P and E whether our stresses are under limits. Let's try to solve that further. Let's try to get that. I would say your final stage is there, that we can write that final stage is there, final stage. So your stresses should be in this way, that this is your final stress condition. And I would say there is live load also. I can write here M live by Z bottom, and there is M live by Z top. Negative, positive. And final stress diagram should be, I want to say whether our stress diagram is in this way. It should not be going out. That means here the stress should not be greater than 15, and here the stress should not be less than 0. We have to ensure that condition. As per the criteria we have. That means the stress should be either less than 15. That means it should not be greater than 15. And here we are saying it should be 0 or it can be greater than 0. That means it should not be less than 0. So we need to check that. We need to check. So for that, let's keep these values as 431.25, and the value of E is 122.33. Okay. And I would say there is some losses also. Final stage would be having some losses. We'd be having some K times B naught. Do we know that? We're having some K times B naught. So I would say there's some K times B naught for all those values of P. K times B naught. So we need to see what is the percentage loss we have. What is the percentage loss we have to take? It's saying that you can have general 20%. You can assume 20%. Let's assume that we have 20% loss. That means K value is 0.8. So let's solve for that. So these equations we know. We need to take those equations and just multiply that K value of 0.8. Your K value of 0.8. So K times. All the stuff is changed from that to K times. And we need to substitute the value of P also. So we have to substitute the value of P also here. Yeah. 431.25 and 122.3. Let's remove it. So first case is there, first case is there. That's first case. We have the equation that's same. Only thing we have to add here effect of the live load for the second case, effect of the live load for the second case, effect of the live load for the second case, effect of the live load for the second case. Okay, let's erase it. Let's erase it. So I would say one more thing here, that's m live by z top, and in this case we have m live by z bottom, and this one is negative, and such that this should be, we want to see how much the value we have in these, because of these resultants we need to see how much is the value. So let's calculate f top. Let's calculate the f top for first case. F top, your f top is p naught. We have to substitute the value of p now. We have to substitute the value of p here. We have to substitute the value of p. Let's have the value of p. We know the value of p. The value of p was 431.25, 431.25 kilonewton, and the value of k, that is 0.8. So this is the equation. This is the first part, that is k times p naught by a. Second part is we have to multiply here 0.8, and the value of e, we have to substitute the value of e, that is 0.13372, and the value of p we have to substitute as 431.25 kilonewton. So all that stuff we have, and rest of the thing is the same. We have to replace this as z top for the first case, z top, that means 133.72, and similarly here we have to replace it as z top for the first case, 133.72, 133.72, and we have to say this is the effect of dead load. This is the effect of dead load. We have to add the live load also. We have to add the live load also. So that's plus m live. The value of live load was, 49.5 kilonewton meters, and divided by 1148.88 10 to the power 6 divided by 133.72. That's your z top, and that we calculate, that comes out to be equals to 5.98 megapascal, 5.98 megapascal. And second stress is that f at the bottom, stress is at the bottom, and that equation we have, if we take this one, we have that value equals to p by a, k times p by a, and k times p naught by a. One more thing is there, k times p naught e by z bottom, and third one is there, k m dead by z bottom, and fourth one is there, m live by z bottom, and this one is negative, negative, positive, positive. So we had to solve for those, and I would take those values here. See, first one is okay, first part is okay, first part is okay as it is. This one is okay, 0.8, that is k times p by a now, k times p by a, that's first part. First part is same. After that we have to add, so we have to write plus, we have to write plus for the second case. So after that we have k times p naught e by z bottom. Here the z bottom, that is 266 point, so z bottom is changed by that because y bottom is different, so 266.25. and for the third one is, we have to also change that 266.25, and all the stuff is same, all the stuff is same, all the stuff is same. Here we have to replace this one, that is 266.25, and the signs we have to change. For the bottom, this is negative, this is also negative, so we have to write this is also negative, this is also negative. And finally your stresses at the bottom, coming out to be equals to 0.08. So final stress diagram would be that there's some 5.98 and there's some value of 0.08. So this is our final stress diagram, and the condition was that you should have a stress in compression as maximum we can take as 15, and in tensile zone we can have either 0 value. So this was the ideal condition from the problem. It was saying that you have to take the stresses, tensile stresses should be greater or equal to 0. So in this case I would say stresses in the tension zone is greater than 0, so satisfied here. And here this condition was stresses in the compression zone, that should be less than 15, and I would say here we have stresses less than 15, that's also satisfied. So your value of P and E is correct, so that you can finally take the value of P and E as per the requirements that P and E we have solved for. Let's take one more problem. Let's say there's some beam. Let's have a different color. Let's say there's a beam. There's a beam having some overhang also. This is 8 meter, and this one is your supported part is 8 meter, and overhang part is 2 meter. And we are placing live load here. Live load throughout the length. Live load of 3.52 kilonewton per meter. And we have the cross section of the beam. We have the cross section of the beam that is 300, 900, 300, 900, and you need to say what's the profile we have to take. Determine the cable profile we have to take. Determine the cable profile, or we can say suggest the cable profile. What is the cable profile we can take? At the rate of size that which balances dead load and live load. Which balances dead load and live load. Dead load and live load. Which balances dead load and live load. And your p value is equals to 500 kilonewton. 500 kilonewton. So all the this is all the stuff that's provided to you. So we need to take that. What should be the cable profile? What should be the cable profile such that balances dead load and live load? So can you calculate dead load first? I would say, what is the dead load? What is the dead load we have? Dead load is 24 kilonewton per meter cube into area of the cross section. That is 6.48 kilonewton per meter. So that if the problem is saying that balances dead load and live load, we can take some of those. I would say, what is the total UDL we can have? That is 3.52 plus 6.48. That is 10 kilonewton per meter. So we got the UDL on the beam. That's 10 kilonewton per meter for this beam, that is overhang beam, such that you should take a cable profile that would balance the dead load and live load moments. How can you solve this? We have already told you that the cable profile is similar to that of the BMD of the beam. That's similar to BMD, and then we place it in the opposite manner, reverse manner. Once we got the BMD, after that we have to place it similar to that but in the opposite manner. That should be the cable profile. That should be our cable profile. So I need to calculate the moment equation. I need to calculate moment equation. I would say, if you have a beam, if you take a beam that's having a final UDL of 10 kilonewton per meter, there's a beam of 10 kilonewton per meter, a UDL having there for the entire section, and we have that simply support beam. Let's say this is support A, support B, support A, support B. If I get the moment equation, if I got the equation of moment in terms of x, and accordingly I can say the equation of that cable profile should be as a function of that moment function. So if I try to solve the equation for bending moment at any section x, can you calculate that? So for that I had to say what is the reaction at either of the supports. 8 meter, this is 2 meter, this is 2 meters. So if I try to calculate what is the reaction at the A by the summation of moments at the point B, so I can solve the reaction A. That let's say the reaction A we can solve, that was coming to be equals to 37.5. Reaction B is coming out to be 62.5. Now if I write the moment equation at any x, if I write the equation for the span AB, if I write the equation, I would say the moment equation would be 37.5 into x minus 10x squared by 2. That's moment equation for this part. And for the second part, I can have equation, because there is some simply support. I can take the equation for this one from this side. I can take for the B, or I can say for the part BC. For the part BC, the moment equation would be in this way somewhere here. I would say the equation would be some wx squared by 2, 10x squared by 2. See, I'm going to cut the section in this way, that this is some moment and there's some w. So they are in the both are in the same direction. So your moment equation here would be minus 10x squared by 2. So this is your moment equation for the two spans. Two sides we have two different equations. Now I need to solve that where is the moment that is maximum? At what location the moment is maximum? If this was simply support beam, I would say that moment is maximum at the midspan. Now for this case overhang, I had to say what is the location for moment to be maximum. I want to solve for that. I would say for moment to be maximum, I have to check that. I have to maximize that function of moment. So I would say if I maximize this part to be maximum, if I want that moment at x to be maximum, I would say your 37.5 is equals to 5. Is it 10? That is 10x. So x equals to 3.75 meters from this side. So your value of x for this case is from this side. So at the value of x equals to 3.75, your moment is maximum when you differentiate that function of moment. Okay, that's your x equals to 3.75. So out of the total 8 meters, at the location of 8 meters, at the location of 3.75, your moment is maximum. Let's try to have that here. Let's try to have it here. So let's say 3.75 is somewhere here. This is 3.75 section. I want to see what is the BMD profile. I would say the moment here is 0 because it's the simply support. Moment here is 0, and we are having a positive moment of, and at that location we need to say what is the moment at the 3.75. We have to substitute what is the moment at 3.75. Let's try to calculate that based on this equation. I would say that is 37.5 into 3.75 minus 10 by 2 x square. So that moment is coming to be equals to 70.31 kilonewton meter. 70.31 kilonewton meter positive. So let's say this is 70.31 kilonewton meter. And tell me what is the variation of the moment? Is it parabolic variation? Is the variation parabolic based on the equation? I think this is parabolic variation. So we have parabolic variation of that x. So I would have the equation of, let's say the moment diagram would be some sort of parabolic, and here we have support, what you call as simple support. So your moment is 0 here. Moment should be 0 here, and I want to say, yeah, moment should not be 0 here because if it is simply support, but we have overhang also, so we need to solve what is the moment at this location. It can't be 0 here because this is overhang, so here we can have moment because of this UDL from the right side. So this diagram should not be correct after that. So this part we have to erase. We need to solve for the moment in the part BC at critical location. Let's solve for that. I would say from this equation, from the second equation, can you tell me what is the moment maximum? So if I substitute value of x equals to 2 meters, I would say moment at B equals to minus 10 by 2 into 2 square. That's minus 20 kilonewton. So negative hogging moment should be there. Hogging moment of 20. Let's say this is 20 negative. So I have to join now in this way. So after that, it goes to 0. Because the equation is parabolic, so we have this equation. We have the diagram in this fashion. This is your BMD. This is BMD. So your profile of the cable should be similar to that, but in the opposite manner. Let's try to have a beam. Let's try to have a bigger beam. Let's try to have a bigger beam. Let's try to have a bigger beam here. Let's say this is your beam, simply supported. Yeah, this one is your overhang. Here we have overhang. This is 8 meter and this one is your 2 meter. And the neutral axis, let's assume that this is neutral axis. And I'm going to have a cable profile exactly in the same fashion. That's a parabolic variation. So I should have a cable profile in this way. Now I want to say what should be my value of this one, what should be this one, and what should be this one. I can call it as E1, E2. We need to solve this E1 and E2. We have to solve these two, E1 and E2. Let's make it as a beautiful one. So this should be the profile of the cable. OMG. Let's have a different color. This should be the cable profile. Now I want to say what is this value of E1 and what is this E2. So based on the concept where it is saying that we have to balance this. We have to balance this. If I apply load balancing concept, if I apply that load balancing concept, it was saying that eccentricity at any location of the cable, eccentricity of that cable from the neutral axis for the cable, that is equals to moment at that section, bending moment at that section divided by the pre-stress load, pre-stress force P. So this is the equation, general equation we have for complete balancing of those loads. So because of those external loads, because of the dead load and live load, we have bending moment at any section. That's BMX. That's external bending moment caused. That's bending moment caused because of the external loads, dead load, live load. So I would say your E at any x is equals to moment at any x divided by your pre-stress force of P. So I have to solve that. Yeah, I know all that stuff. So I would say your eccentricity at the location of that 3.75. I kept it as E1, and that is moment 1. What is the moment there? 70.31. This is the moment here, 70.31 divided by the value of P. Pre-stress force was given to you as 500 kilonewton, so 500 kilonewton, and your eccentricity E1 is coming to be 140.6 millimeters. And your eccentricity at the overhang part, I wrote that as E2, and that is moment 2, that is minus 20 kilonewton meter divided by the value of pre-stress force, 500 kilonewton. And this one is your negative times minus, I would say, minus 40 millimeters. Negative means, what this negative means, it means your cable is above the neutral axis. It's above the neutral axis. And first one is there below the neutral axis. This one is below the neutral axis. So let's take those two values, 140.6 minus 40. So your eccentricity one is 140.6 and this one is your minus 40. So this is the cable profile we have for this beam. Okay. And I would say cable is having that eccentricity 0 at the ends, because moment is 0 at the ends. So your eccentricity of the cable at the ends, E0, and I can say E10 is equals to 0. So this is your E0, E10. So this is our cable profile finally. Okay, let's take one more final problem related to that transfer stage. Let's go. So we have a beam, simply support beam. We have a simply support beam, 15 meters, simply support beam, 15 meters. And cable is parabolic. And the value of E at the midpoint, is, this is the eccentricity at, I can say this is EP. Okay. So we need to solve the value of EP, but the condition is that we have a UDL live load of 60 kilonewton per meter. 60 kilonewton per meter live load. And the cross section of the beam is T section. We have a T section beam. T section pre-stress beam, and top width is 1000, and this one is 400. This part is 500, and this is 800. This is your 800. This is 800. Okay, and it's given that at the midspan, your cable is placed from the soffit at a location of 200 millimeters. So this part is 200 millimeters. Your cable is placed here at 200 millimeters from the bottom. So I had to say what is the value of EP. For that I had to calculate neutral axis. So I had to say neutral axis is somewhere. Let's say neutral axis is somewhere here. This is neutral axis, and I want to say what is this value of EP? Okay. Now the problem is saying that, what is the problem saying? we have a loss percentage of 15 percentage loss of the stress, that is 15%, 15% at the final stage. That we are saying this is at the final stage, and actually it's summation of all those losses that have started from during the tensioning of the steel wires to the transfer of the steel stress from steel to concrete. So that's the sum of all those losses. And we have the cable. Area of the cable is 3200 millimeter square, and your stress in the cables P0 initial stress was 1500 megapascal. So your initial pre-stress force would be, that is 32 into 15, that is I think 48. Your initial force, your pre-stress force would be equals to 4800 kilonewton, and final force, I would say P final would be K times P0. So your value would be 0.854800. So that's 4080 kilonewton. So you had to calculate with this part we calculated. Okay. Now what is the thing we have to calculate? It's saying that get the stresses in the stage 1 and stage 2 at the midspan. So we have to calculate stresses on the midspan section, that's at the top and bottom, but for the two different cases, that is, one is your transfer stage and next one is that final stage. So let's go for those two. For first thing is that we had to calculate the neutral axis location. Neutral axis location. Yeah. Neutral axis location we had to solve. Let's go for, I would say this is y top. That can be solved as 1000 into 400, isn't acting at 200, plus second area is there 800 into 50, 500, acting at 400 plus 400, that is 800, divided by total area of the cross section, that's 800,000. So that is the total area of the cross section, and your value of y top is coming to be equals to 500 millimeters. So y top is 500 millimeters. That means if this is 400 and this is 100, that means the y bottom is 800 minus 100, that is 700. So y bottom is 700. So can you get the value of eccentricity now? If this is 200, that means this part is 500. Eccentricity is 500. Can I say eccentricity from the neutral axis is 500 millimeters. So finally, all need is that y top, y bottom, and EP. Y top, y bottom, EP. Let's go for that now. Let's take the first case that we have transfer stage. First stage, that is transfer stage. I would say there is some section on that we are applying some pre-stress force of P at some eccentricity of E. So I have to solve that stresses. First one is that throughout the fibers we have constant stress of P0 by area cross section, and second one is there top tensile, bottom compressive, because hogging moment is because of that P into E, hogging moment. So P into E, negative, positive, P0 EP by Z bottom, P0 EP EP by Z top. And third one we have to take that because of the dead load. That is top compressive, bottom tensile. That is M dead by Z top. This is M dead by Z bottom. Okay. So we have to solve those values. What is the dead moment? What is that moment D because of the dead load? So let's take the dead load calculations. Dead load WD is equals to 25. Should we take 25? Yeah. 25 into area of the cross section was 800,000 millimeters square. So that is a final value of 20 kilonewton per meter. And because of that, you would having some dead moment, that is 562.5 kilonewton meters. And because of the live load, you are having some moment contributed, that is 1687.5 kilonewton meters. That equation is WL square by 8 at the midspan. So these are the two different moments. So I would solve that 562.5. I would say this is 562.5 kilonewton meters divided by I neutral axis. you have to solve the value of I neutral axis. Can you solve the value of I neutral axis? Can you solve the value of I neutral axis? I neutral axis. So I had to solve that I neutral axis. That's BD cube by 12. BD cube by 12 plus AD square. AD square. The centroid from the top is 4. This was 500. This was 500. So I would say 500 minus 200 whole square. And third area is there. That's BD cube by 12. BD cube by 12 and plus BD square. That's AD square. AD square. Your centroid is from the bottom. I would say centroid is at 400, but your location of neutral axis is at 700 from the bottom. So this should be 300 square. I think it should be 300 square. Yeah, this should be 300 square. So based on this calculation, we can say that final value of I is that 9.867 10 to the power 4, 10 to the power 10 millimeter power 4. So we have to use those values to get the value of Z top and Z bottom. Now I'm going to write it. I'm going to write the equation. What is the value of P we have? Initial value of P 4800 kilonewton without the losses, 4800 kilonewton. So I can write the stresses here, 4800 kilonewton divided by the area of the cross section. That was 80,000 some value, 80,000. That was some 80,000 value, 800,000 millimeter square. And second stress is there, P naught EP by, let's calculate for the top. Then let's say this is F top. At the top we have positive, then after that we have negative, and that is P naught EP by Z top. P naught EP, what is the value of EP? The value of EP is 500. Value of EP is 500. So EP by Z top. Z top is I neutral axis divided by Y top. That is 500 millimeters. So you have to ensure that units are in a correct way. Then after that, third stress is because of the dead loads. So that's plus. At the top we have positive. For the top we have positive. Okay. That's 562.5 10 to the power 6 Newton millimeters divided by I neutral axis divided by Y top. That is 500 millimeters. So you can solve the stresses. That comes out to be equal to final value of F top minus times 3.311 megapascal. And stresses at the bottom would be P by A, that is same value, P by A, that same value here, P by A. Then after that would be having positive stresses at the bottom, that's positive. After that we have negative. So this is positive value and this one is negative. But here the value thing is that we are going to change that Z bottom. So this is going to change by, we have to replace it as Y bottom. This part we have to replace by Y bottom, and the value of Y bottom is 700 millimeters. So after that we have the calculations. And this value is that 19.0316 megapascal. So after that I can have the stress diagram. I can have a stress variation diagram. So this is your minus 3.311, and this side we have 19 point some value. So this is our stress diagram for the transfer stage. So let's take the second stage, that is final stage, with the value of P final as 4080. We can directly take that as 4080. Let's take the second case, that's we have some P final. We have some final force of PF. We have some final force of PF. So I can write that final value is 4080. This is also 4080. All the stuff is same except we have to change that Z top, Z bottom accordingly, and all that stuff is same. So I would say your stress at the top is equal to 6.164 megapascals. Stresses at the bottom is 3.61 megapascals. So final diagram is in this way. This is your final diagram for the stresses. So that was the end for that topic. Thank you for watching these problems, watching these different stages of stress analysis for your pre-stress concrete. beams.